Well, hey there. This is Chris Clements, Caddo Magnet High School. This is my first podcast of the 2008 and 09 school year. I started doing podcasts in February of 2008, so what I'm doing is catching up to February. So I hopefully won't have to redo too many of them, but this will be my first real topic in my Chemistry 1 classes, and it will be on significant figures, units, and density. So the way this works is you have a podcast that is known as an enhanced podcast, and with an enhanced podcast you have chapter markers that will allow you to go to specific points within the podcast based upon the content there. I have converted PowerPoint shows into JPEGs or pictures, and I've embedded those JPEGs at appropriate points within the audio part of the podcast. So all you have to do is once iTunes begins this podcast, you'll see that there's a choice of chapters on your menu up top, and you can choose whatever chapter you want. So I will set up the chapters for you once I'm through recording this and make it very logical. All right, let's go ahead and get started. And again, this is on significant figures, units, and density. We'll be doing lots of conversions in here as well. So the first thing we're going to go over are those goofy things called significant figures. Now, a lot of folks get confused by this, but let me tell you, the real use of significant figures comes in making measurements. A lot of folks don't see the use because they don't use different measuring devices. However, when you use different measuring devices within a laboratory setting, significant figures become very important, and your calculations rely upon your number of significant figures. So let's first go over how we identify whether a figure is considered to be significant or not. And by the way, if it is not considered to be significant, it does not mean that we get rid of it. So there are several rules that allow us to determine what is a significant figure and what is not. The first of them is very straightforward. It is that non-zero integers are significant. So any number that is not a zero is always considered to be significant, regardless of where it is within a representative number. The trick with these comes when we have zeros. So we have three classifications of zeros. We have leading zeros, captive zeros, and trailing zeros, and each of them has its own rule for determining significance. Leading zeros are never significant. They are known typically by mathematicians as placeholders. An example would be 0.01. There are two leading zeros in that number. There's one non-zero integer. Therefore, in that number, 0.01, there is only one significant figure. Captive zeros are pretty much what they sound like. They are zeros that are caught in between a couple of non-zero integers. You can have an infinite number of captive zeros. It's not necessary that you have one zero sandwiched by two non-zero integers. You can have, again, an infinite number of zeros sandwiched by non-zero integers. So in the number 101, there is a captive zero, and captive zeros are always significant. The ones in that number are also significant because they are non-zero integers. So that means I have three significant figures in that value 101. In the value 1001, I have four significant figures because both of the zeros are captive zeros, which means they are significant, and the ones, being non-zero integers, are significant. If I have the number 0.0203, again 0.0203. There are two leading zeros. They are not significant. There's one captive zero, and there are two non-zero integers. So that value, 0.0203, has three significant figures. And then the third type of zero is called a trailing zero. Trailing zeros are only significant when there is a decimal present anywhere in the number. It doesn't have to be to the left or to the right of the decimal, one or the other. It is if there's a decimal anywhere in the number and there's a trailing zero, which as its name implies indicates it's at the end of a value, then that trailing zero will be significant. However, if there's no decimal present in the number anywhere, then trailing zeros are not significant. So a couple of examples of that are in the number 500. 500. There's no decimal. There's an understood decimal after the second zero, but it's not present. I didn't say 500 decimal or 500 point. So in the number 500, there's a 5 and there are 2 trailing zeros. The trailing zeros are not significant because there's no decimal in the number. However, if I do this goofy scientific thing that you don't see too often in math classes and I make it 500 point, that tells you that I measured that, or that I counted that actual value. Meaning if I tell you the population of a classroom is 500 people, you might think that I rounded that number, or I guesstimated that number. Well, if I say it's 500 point people, it's telling you I counted that number. And that makes those trailing zeros, both of them, significant. So in the number 500 point, there are 3 significant figures. The 5 is significant, and both of the zeros, which are trailing zeros with a decimal present in the number, are significant. Then a little addendum to these significant figure rules is that exact numbers have an infinite number of significant figures. So if I tell you that I have a dozen eggs, we all know that that means I have 12 eggs. It doesn't mean that I have 12 point eggs. It doesn't mean that I have 12.000 eggs. It means that I have exactly 12 eggs. And if I wanted to consider the number of significant figures, that number would go on and on and on and on and on, because the number is actually 12.000 ad infinitum, meaning going on to infinity. So we don't say, when I give you that there are a dozen eggs, that we have an infinite number of significant figures. We don't ask for the number of significant figures in an exact number like that. All right, let's get some practice with significant figures. On this slide, you see 6 numbers with varying levels of significant figures. Let's take each one of them at a time and analyze it. In the first bulleted number, you have 60.0000. The 6 is significant because it's a non-zero integer. And then our question comes into play with the zeros. There are 5 zeros in this number, and every one of them is a trailing zero because they are to the right of a non-zero number. There is a decimal in the number, so now we have 5 trailing zeros with a decimal in the number and 1 non-zero integer. That means in that particular example, there are 6 significant figures. The next one is 400,000. Well, there's no decimal in the number. The 4 is significant. There are 5 trailing zeros, but they're not significant because there is no decimal in the number. We again know that there's an understood decimal at the end of that value, but we don't see it, which means we cannot imagine that it's there. So in that example, 400,000, there's only 1 significant figure. In the number 7.023, you have 3 non-zero integers and you have 1 captive zero. Captive zeros are always significant, so in this example we have 4 significant figures. The next value is 0.090. You have 2 leading zeros, which are never significant. You have 1 trailing zero and 1 non-zero integer. The trailing zero will end up being significant because there's a decimal in the number. Again, it doesn't matter where the decimal is, as long as you have a trailing zero with a decimal anywhere in the number, that trailing zero is considered to be significant. The next one is 0.0002. All 4 of those zeros are leading zeros. Leading zeros are never significant, so the only significant figure in that value is the integer 2, and therefore there's only 1 significant figure in that example. And then I'll give you an example of a number written in scientific notation. Now, when I write a number in scientific notation, as I will do throughout this school year, you do not consider the power of 10 to be a part of the of the value in determining the number of significant figures. So when I look at 3.05 times 10 to the 5th, the only number that I look at is the mantissa, the 3.05 portion, to determine the number of significant figures. I don't translate this into regular notation and then put it back into scientific notation. I only look at the mantissa, in this case the 3.05. And when I see that number, there is a captive zero, there are 2 non-zero numbers, which means that I have 3 significant figures in that example. Alrighty, we do have rules for addition and subtraction and for multiplying and dividing. They're called significant figure rules, but with the addition and subtraction, it's a little misleading because we really don't pay attention to significant figures when we add and subtract. So I'm going to give you the rule. It can be kind of verbose, and then we'll go over 2 examples. The answer, meaning your sum or your difference, has the same number of decimal places as your least precise measurement. Well, this gets into a discussion of precision, and I'll discuss this a little further later, but just to remind you, a number that goes out to a farther decimal place is more precise than a number that doesn't go to as far a decimal place. So 1.0 is more precise than 1, and 1.000 is more precise than 1.0. So when I look at my 2 examples and I have 7.2 plus 4.841, the number that is less precise of those 2 is 7.2. It is only carried out to the 10th place. What that means is that my answer, in this case my sum, will only be carried out to the 10th place. Notice I've not mentioned anything about significant figures in this. So the way to work problems like this when you're only adding and subtracting is go ahead and add your values for this example, 7.2 plus 4.841, and get your value without rounding. And when I do that, I get 12.041. But I now need to look at the rule that says my answer will have the same number of decimal places as my least precise measurement. We said 7.2 was less precise than 4.841. Therefore, I need to round 12.041 to the 10th place. So I use rounding rules that I've kept in my mind since, I don't know, when did y'all learn those? In elementary school, where if it's 5 or greater, you round up. If it's less than 5, you keep it the same. So I will round 12.041 to 12.0. In my subtraction example, I have 3.142 minus 1. Well, of those 2 values, 1 is less precise, carried out to the ones place, than 3.142. That means my answer needs to be rounded to the ones place. Before I do any rounding, I get 2.142. Not heavy-duty math here, is it? And then I round to the appropriate place using appropriate rounding rules. So 2.142 would round to give me 2. Again, where this comes into play is when we use different measuring devices. When we use, say, an analytical balance, which carries a mass out to the 10,000ths of a gram, and a triple beam balance, which carries it to the hundredths place of a gram. And we want to get an average mass of something. That is an example of where we use this, so don't get too frustrated with this. Alright, the multiplication and division rule actually does have you pay attention to the number of significant figures, and it states that the number of significant figures in the answer can be no greater than the number of significant figures in the value with the least number of significant figures. Again, pretty darn verbose, but we'll work it out. Notice I was lazy and I used the same numbers as on the previous slide, and I just replaced a plus sign with the multiplication sign and a minus sign with the division sign. You like that? I'm pretty crafty that way. Alright, so in this particular case, we need to look at our values that are being multiplied or divided and determine who has fewer significant figures. Of 7.2 and 4.841, 7.2 has fewer significant figures with 2 significant figures. 4.841 has 4 significant figures. What that tells me is that my product in this particular case will have only 2 significant figures. So I take 7.2 and multiply 4.841. And I get, before I do any rounding, 34.8552. Now, my value in my answer can only have 2 significant figures, and I'm going to use proper rounding rules. So 34.8552 rounded to only 2 significant figures will give me 35. When I take 3.142 and divide by 1, can you do that one in your head? I need to pay attention to the fact that 1 has only 1 significant figure. Therefore, my answer can have only 1 significant figure. So before I do any rounding, my answer is 3.142. And when I round appropriately to only 1 significant figure, my answer is 3. We'll come back and do some more practice on significant figure stuff, but I want to get a few more items in here. So let's first look at temperature conversions, Fahrenheit to Celsius and Celsius to Fahrenheit. And I'm sure you've been exposed to this at some point and know that there's a minus 32 in there somewhere, and there's a, I don't know, 5/9 and 9/5, and you don't really know what to do when. Well, what it's based upon is the boiling point and freezing point of water on the Fahrenheit and Celsius scales. And when I teach this in my classroom, I do show this in much more detailed fashion, but I'm just going to kind of briefly go over it here. What it works out to be is that for every 100 degrees Celsius that you have, if you had the two scales side by side, for every 100 degrees Celsius, you would have 180 degrees Fahrenheit. And if you reduce that ratio, 100 to 180, you will get 5 to 9. So that's where the 5/9 and 9/5 stuff comes from, that you have 5 degrees Celsius for every 9 degrees Fahrenheit. While the minus 32 and plus 32 business comes from the difference in the freezing points of water on the two scales. The freezing point of water on the Celsius scale is 0 degrees Celsius. On the Fahrenheit scale, it is 32 degrees Fahrenheit. So what you have to do is account for that difference in the starting points of the two scales by either subtracting 32 degrees Fahrenheit if you begin with the Fahrenheit temperature, or adding 32 degrees Fahrenheit if you're trying to convert Celsius to a Fahrenheit temperature. So let's do a couple of examples using the formulas that I have here. If I give you, I don't know, let's say a typical oven temperature of 350 degrees Fahrenheit. And my first step is to subtract 32 degrees Fahrenheit. Notice you can subtract like units. I get a value of 318 degrees Fahrenheit. I will then multiply that value by 5 degrees Celsius and divide by 9 degrees Fahrenheit. Now, what you should have learned at some point in your scientific career up to now is that you can divide out like units. So what I'm going to have is 318 degrees Fahrenheit times 5 degrees Celsius over 9 degrees Fahrenheit. My Fahrenheit units will divide out, and I will be left with degrees Celsius. So once I perform the actual math associated with this, and we are going to round to the same number of significant figures that we started with, which was 350 degrees Fahrenheit, remember? I didn't say point, so we are going to round to two significant figures. And though I get 176.66 on and on and on, I'm going to round that to 180 degrees Celsius. Okay, let's do a reverse process of that, and let's take a Celsius temperature of, say, 25 degrees Celsius and convert it to Fahrenheit. So this time I'm actually going to convert from Celsius to Fahrenheit degrees, or think I'm converting, before I mess with the 32 degrees Fahrenheit. Remember, you can't mess with the 32 degrees Fahrenheit because it's subtracted or added until you're dealing with degrees Fahrenheit. You cannot subtract or add unlike units. So I take 25 degrees Celsius and I multiply by 9 degrees Fahrenheit over 5 degrees Celsius. My Celsius units divide out, and I end up with 45 degrees Fahrenheit. But that's not the actual Fahrenheit temperature. So I then add 32 to that, and I end up with 77. Again, starting with my number of significant figures, 77 degrees Fahrenheit. We're not going to pay attention to the number of significant figures in the 5 degrees Celsius, the 9 degrees Fahrenheit, or the 32 degrees Fahrenheit, because those are exact numbers. And remember, those have an infinite number of significant figures. The third temperature scale that we'll certainly be using in chemistry throughout this year is the Kelvin scale. It's known as the absolute zero temperature scale because at 0 Kelvin you have no movement. Nothing can get any colder than 0 Kelvin. It's still a theoretical temperature. They've gotten pretty close to it, but not quite down to exactly 0 Kelvin. It doesn't carry a degree sign with it. That degree sign was abolished by the International Union of Pure and Applied Chemistry, which is known as the IUPAC. Sometime back in 1984, they just got together and decided, hey, let's get rid of that degree sign with Kelvin. So we don't say degrees Kelvin. So let's take your Celsius temperature that we started with in the second example, 25 degrees Celsius, and let's convert it to Kelvin. It's a very easy process. All you do is add 25 to 273, and that is the magical conversion to Kelvin, and that means it is 298 Kelvin. And let's take 0 Kelvin and determine what degrees Celsius that is. That means you're going to take 0 Kelvin, subtract 273, so that your absolute zero temperature on the Celsius scale is negative 273 degrees Celsius. Again, we'll be using that Kelvin scale quite a lot, especially when we get into gas laws later in the year. Okay, let's go back to some significant figure practice. And with each of these, A through H, let's go through and state how many significant figures there are, and then I'll have you do something else with these numbers. So when I look at and by the way, if you want to stop the PowerPoint the PowerPoint and the podcast at this point and do these, that's going to be helpful, because I'm going to kind of rip through these. I'm not going to take as much time as I did, and then you can come back and listen to me and check what your answers are. Does that sound okay to you? All right, on A, 900.0, there are 4 significant figures. On B, 3.0020, there are 5 significant figures. C is 6.020 times 10 to the negative second. There are 4 significant figures. D, 2007. There are 4 significant figures. E, 6 times 10 to the fifth. There's 1 significant figure. F, 47,000. There are 2 significant figures. G, 0.0001. There is 1 significant figure. And H, 0.0098030. There are 5 significant figures. The next thing I ask you to do is round those same numbers to 3 significant figures. That seems to be the most common number of significant figures you will be presented in problems within chemistry. For example, on the AP chemistry exam, which none of you needs to worry about at this point, but on that AP chemistry exam, they tend to have you work out problems such that you end up with 3 significant figures. So that's why you hear chemistry teachers so often say, oh, round to 3 significant figures, because that's what we tend to do. Again, if you want to stop the PowerPoint and podcast at this point, you're certainly welcome to do so. I'm going to go through what these values would be when rounded to 3 significant figures, and on some of them there are a couple of ways to do it. Sometimes you have to convert from regular notation into scientific notation. Keep that in mind, or vice versa. What you want to focus on is keeping the value of the number as close to its actual value as possible. A way that I think you can visualize that is to put a dollar sign out in front of these numbers and see if that helps you keep the value the same. Okay, if you've stopped and rounded each of those to 3 significant figures and want your answers, here you go. You take the number 900.0, which had 4 significant figures, and round it to 3 significant figures by writing 900 point. Again, that's an unusual thing to do, but we do that in science quite a lot. An alternate method is to convert it to scientific notation and make it 9.00 times 10 to the second. On B, 3.0020 had 5 significant figures, and we want it to have 3 significant figures. So we can just write it as 3.00. Again, consider your rounding, consider your value. C, 6.020 times 10 to the negative second, had 4 significant figures in it. We want it to have 3, so we make it 6.02 times 10 to the negative second. If you wanted to convert that one to regular notation, you certainly could have, and it would be 0.0602, still having 3 significant figures. On D, 2007, again, 4 significant figures, we want 3 significant figures. So I, again, need to consider the value. I don't just want to lop off the 7 and make it 201, because I think you'd agree with me, $2,007 is a lot more money than 201. You're not keeping the value the same if you just lop off the number. So what I want to do is round it to 2010, 2010. When I do that, I have 3 significant figures. An alternate way is to put it in scientific notation, make it 2.01 times 10 to the third. On E, 6 times 10 to the 5th has one significant figure. To make it have 3 significant figures, I can add zeros. It's not a really appropriate thing to do in measurements, by the way. You cannot just add zeros and make an assumption that they were measured. But in this example, we would do so by making it 6.00 times 10 to the 5th. On F, 47,000 has 2 significant figures. To make it have 3 significant figures, I would convert this into scientific notation. So I would have 4.70 times 10 to the 4th. On G, I would do the same thing I did in E, which is to add zeros at the end. Again, it's not an appropriate thing to do. If I've made that measurement to be 1/10,000th of a gram, for example, I can't just add zeros to the end. It's inappropriate. But I'm not giving you units or anything with these numbers, so we're just going to pretend like we can do this. So on G, you would make it 0.000100. You could put that in scientific notation as well as 1.00 times 10 to the negative 4th. And on H, 0.0098030 has 5 significant figures. To make it have 3, I round and truncate 0.00980. Putting it in scientific notation is always appropriate in this one, so 9.80 times 10 to the negative 3rd. Okay, and then I have a few more practice problems for your addition, subtraction, multiplication, and division. Again, if you want to stop the podcast in PowerPoint, do so, perform these operations, and then come back and check them, because I'm just going to calculate them and give you the appropriate answer. So in A, 2.0 plus 1.650 should be rounded to the tenths place and give you 3.7. B, 12 minus 0.00999 should be rounded to the ones place so that my answer is 12. On C, 8.040 times 10 to the negative 3rd. And by the way, in my classroom I do go over how to input this into a calculator, but it's a little befuddling, I'd say, if I were to do it now. I'm going to multiply that by 9 times 10 to the 6th. And I need to round to the ones place. So I end up with 7.2360 times 10 to the 4th. Before I do any rounding, I would round that to 7 times 10 to the 4th. Alrighty, and then 400 divided by 3.5. I'm sorry, in C, it wasn't rounding to the ones place, it was rounding to one significant figure, so I should have had 7 times 10 to the 4th, as I said, but it was because of significant figures. See, we all make some mistakes here and again. Alright, 400 divided by 3.5. 400 only has one significant figure, so I round my value that I get to 100. Okay, now we're going to look at how we make measurements, what units we use, and how we do metric conversions, that kind of stuff. This is going to end up being a fairly lengthy podcast. Not all of them will be this long, by the way. Alright, so I've given you on this slide what are known as System International, or SI units of measurement, for 5 very appropriate measurements that we will make throughout chemistry. For mass, the SI unit is kilogram. That doesn't mean that every mass measurement we make will be made in kilograms. It's not appropriate, for example, to measure the mass of an aspirin tablet in kilograms. You would tend to measure that in grams or milligrams. But I'm just telling what the SI unit is. Length is meters. Time is seconds. Temperature is Kelvin. And the amount of a substance is a mole. What you see on this screen are the abbreviations for each of those measurements. I've given you measurement prefixes that we can apply to any base unit. Base units being things like gram, liter, meter, second, mole, those types of things. And this may look very strange to you and seemingly backwards, but I set it up like this so that you can also write it down as kind of a number line. So that when you see giga, and yes, it's really pronounced giga, and second pronunciation, but not the preferred, is giga. Abbreviated by an uppercase G, I have 10 to the negative ninth, which means that if I have 1 gram, I will have 1 times 10 to the negative ninth gigagrams. That's how I want you to read this. Each of these is relative to having 1 of something. Oops, and I do see a mistake, and I'll correct it in just a moment. I will definitely have that corrected. Shoot, I'm sorry. You're just going to have to correct it on this because I've gone to too much trouble to convert these, but I'll correct it within my classroom. How's that? The next one I have is mega, abbreviated by an uppercase M. And what I get from that is that 1 gram is equal to 1 times 10 to the negative 6 megagrams, and so on and so on. So with each of these, I'm just going to go over how to say it, what the abbreviation is, and the value. Kilo's abbreviation is a lowercase k, and you will have 1 times 10 to the negative third kilometers in every 1 meter. Hecto is a lowercase h. You will have 1 times 10 to the negative second hectoliters in every liter. Deca is lowercase da, 1 times 10 to the negative first. Decagrams would be found in every gram. So I'd said that there was a mistake in here, but I went back and corrected it, which means that you don't have to worry about the mistake, and where it was there, you have deci, lowercase d, which is 10 to the first, or 10 decigrams. Centi, lowercase c, when I have a liter, I'll have 1 times 10 to the second centiliters. Milli is a lowercase m. When I have 1 second, I will have 1 times 10 to the third milliseconds. Micro is a Greek letter mu. It looks like a backwards Y. And when I have 1, let's see what I want to use, mole, I will have 1 times 10 to the 6th micromoles. And then nano, lowercase n, when I have 1 gram, I'll have 1 times 10 to the 9th nanograms. There are certainly more prefixes than this, but these are the ones that we typically would use more often. As we encounter more stuff in chemistry, I'll introduce a few more prefixes, but these will work for most of what we do. Alrighty, what we need to discuss next is what I kind of got a little bit into earlier, accuracy and precision, and then random error and systematic error. Accuracy is defined as how close to an actual measurement your value is. That means you need to know an accepted measurement. If I'm putting a standard mass on a balance that is a 1 gram mass, and the balance reads analytical balance 1.000 grams, it's an accurate balance. If it reads 0.8794 grams, it's an inaccurate balance. Precision is defined in one of 2 ways. Again, I've already gone over one way, which is how far out a decimal is carried. The more to the right you see numbers carried, the more precise those numbers are. An alternate way to look at precision is how repeatable your measurements are. If I put that 1 gram standard mass on a balance and over and over and over, I get 1.000 grams. Then it's precise and it's accurate. If I put it on that balance and over and over and over, I get 0.9000, 0.9000, and so on and so on. It's precise, but it's inaccurate. And if I get in 3 tries 0.5010, 1.000, and 1.204, it's all over the place. It's inaccurate and it's imprecise. So that brings us to random error and systematic error. A random error is typically regarded as human error, which is very easy to do, say, when you're reading a volume. You need to be at eye level with the bottom of a meniscus. I'll go over this in greater detail in my classroom as well when you read a volume. So, for example, if you're holding a graduated cylinder and you're holding it down in your foot above where the meniscus is with your eye level, you're not going to be able to give the proper volume. And if you have different people, for example, measuring volumes, you invite a lot of random error because different people can read different volumes. I do a laboratory exercise in my Chemistry 1 class where we show that. It's a very impressive thing to realize that we can read volumes differently that are all the same volume. And then systematic error is typically regarded as machine error. It would be something like the balance is not calibrated so that it's always off by a certain amount. And in some cases, that's an okay error to have. It depends on what we're doing with our measurements. But hope you understand the differences between those. Okay, we're going to look at a few metric to metric conversions right now, and I would like you to convert 360 millimeters to meters. The way that I prefer you do this is using dimensional analysis, which means I want you to understand the relationship between meters and millimeters. Remember, I gave a reference to 1 of a base unit earlier? So I want you to kind of get in your head at this point that 1 meter is 1 times 10 to the third millimeters. So when you set that up mathematically, I want you to write 360 millimeters, and then I want you to write times. I want you to fill in your units first, where you will decide that you want to divide out millimeters, so put that in the denominator, draw your line, and in the numerator, you want to turn it into meters. So now you have 360 millimeters times meters over millimeters. And now you need to fill in the numbers that are appropriate for the meters and millimeters. And again, I already said 1 meter equals 1 times 10 to the third millimeters. So at this point, you should have 360 millimeters times 1 meter divided by 1 times 10 to the third millimeters. Notice your millimeters will divide out, and you will end up with 3.60, if you want to have 3 significant figures, times 10 to the negative first meters, or if you want it in regular notation, that's fine, 0.360 meters. The next one is 4.25 times 10 to the negative fifth megaliters, converted to milliliters. In this one, I might do it in 2 steps, and I would say 4.25 times 10 to the negative fifth megaliters times, have in my denominator megaliters, and in my numerator liters, times, in my next denominator, liters, and in my next numerator, milliliters. And then fill in my numbers. I know that when I have 1 liter, I will have 1 times 10 to the negative sixth of a megaliter. I know that when I have 1 liter, I will have 1 times 10 to the third milliliters. So then when I actually calculate that, and I have 4.25 times 10 to the negative fifth, what I do is multiply everything in my numerator and then hit divide, and if there are multiple things in my denominator that I need to put in my calculator, I use parentheses. So in this case, I only have 1 thing in my denominator that I have to concentrate on, so I'm going to say 4.25 times 10 to the negative fifth times 1 times 10 to the third divided by 1 times 10 to the negative sixth. And I get 4.25 times 10 to the negative second milliliters. And I will get 4.25 times 10 to the fourth, or 42,500. You can do regular or scientific notation, it really doesn't matter. Already on the third one on this slide, 325 milligrams converted to kilograms. Again, I would tend to do this one in 2 steps. 325 milligrams times milligrams in my denominator, grams in my numerator, times grams in my denominator, kilograms in my numerator. This is much more easily seen, by the way, if I were writing it out. I'm just not doing a vodcast of this where you would see me writing it out, because it would be an enormous file, and I really don't have that much space on my web page. So I apologize for not writing this out, but it's the benefit of being in a classroom. So in that case, I'd fill in my numbers, and I would have 1 gram equals 1 times 10 to the third milligrams. So 1 gram over 1 times 10 to the third milligrams, and then 1 gram in the denominator, and 1 times 10 to the negative third kilograms. So then I type in 325 times 1 times 10 to the negative third. Give me a moment here. And then divided by 1 times 10 to the third. And I end up getting 3.25 times 10 to the negative fourth kilograms, or 0.000325. Alrighty. Voice is getting a little tired. Again, I told you this one was going to be a long one, but it's your first one for the school year for those of you who are my kiddos, and just want to help you as much as I can with these. Alrighty, we're going to look at some metric to English conversions, and in doing so I need to give you what are known as conversion factors. So I will do so for each of these, and I'll pick the conversion factor I want you to use. Some of you may know different conversion factors, but I want you to use the ones that I give you. So in this first example, 360 millimeters equals how many inches? I want you to understand that there will be, for every 1 inch, 2.54 centimeters. So then I want you to use dimensional analysis to go ahead and work through that. And again, this is the kind of stuff that it takes my showing you how to do. So what I'm going to do is just go ahead and let you have time to work it, and then I'm going to give you the answers, okay? And I work this out in class. If you're listening to it and you don't have me as a teacher, then just think about setting it up so that you have your beginning unit, and you want to divide out the appropriate units to end up getting to what you wish to end. Okay, so again, I have to give you conversion factors, and I would prefer that you use the ones that I give you. In this first example, 360 millimeters to inches, I told you that I would like for you to use the fact that 1 inch equals 2.54 centimeters. In doing so, using dimensional analysis, dividing out your units, moving through it progressively, again, in my classroom I show this, you should be getting 14.2 inches. I'm just going to give you 3 significant figures in each of these answers, by the way. In the second example, converting 4.25 times 10 to the negative 5th megaliters into gallons, I'd like for you to use 2 conversion factors. One is 1 liter equals 1.06 gallon, 1 liter equals 1.06 quarts, and then 4 quarts equals 1 gallon. I would think most of you know 4 quarts equals a gallon, but just making sure here. The answer you should get is 1.80 times 10 to the second. On the third one, 325 milligrams equals how many pounds? I would like for you to use the conversion factor that 1 pound equals 454 grams. In doing so, you should get your answer to be 7.16 times 10 to the negative 4th of a pound. And then on the last one, it's a multi-step, and you have numerator and denominator and you're given information. So be very careful with that. The way I have it written on the slide is as a / I do not recommend that at all. I recommend that you write 100 meters and then over, meaning a horizontal line, 1 second. So the conversion factor I'd like for you to use on that is 1 mile equals 1.61 kilometers, or you could use 1 mile equals 1,610 meters, either one. You should know how many seconds are in an hour, or be able to figure that one out pretty easily. And the answer you should get is 224 miles per hour. What I'd like for you to do, if you've not already done so, is just work those out, check your answers, see what you can do. You can certainly email me with any questions that you have on these. I just know that I don't have the capacity to show this in a vodcast and writing on my tablet PC at this point. The last bit of this podcast is going over the concept of density. Density, as you've learned many times in your life, I'm sure, is defined as the amount of stuff in a certain amount of space. And more eloquently, we define that as the mass of an object divided by that object's volume. It can have multiple units. The idea is that you have a mass unit in the numerator and a volume unit in the denominator. So again, there are no set units for density. If we use the SI unit for mass and the SI unit for volume, it would be kilograms per decimeter cubed, which you don't see too often, by the way. I've given you the volumes of a rectangular prism, cylinder, and sphere formulas on this slide, because you're going to use those in the subsequent slides to be able to work some problems. And I'm going to do the same sort of thing, ask you to stop, work them out, and then come back and check your answers. Okie doke. So, volume of a rectangular prism is length times width times height. Volume of a cylinder is pi r squared times height, and use pi as 22 over 7, 3.14. It doesn't matter. You can get essentially the same answer. And the volume of a sphere is 4/3 times pi r cubed. Alrighty. The first problem given information is there. I want you to work through it, see what you get. I'm going to ask you to stop the podcast, work it, and then come back and I'll tell you what your answer is. Okie doke? So that's what we're going to do with each of the 3 problems on these last 3 slides. Okay, so hopefully you've taken the time to work out these 3 density problems. And in the first one, the square piece of cobalt glass with a mass of 12.228 grams. Its dimensions are 50 millimeters by 50 millimeters by 2 millimeters. And I want its density in grams per centimeter cubed. Well, the easiest thing to do is convert those millimeters dimensions into centimeters before you start to calculate the volume of the piece of glass. So when you do that and then you calculate your density in grams per cubic centimeter, you should be getting 2.45 grams per cubic centimeter. On the next problem, where you have a cylindrical piece of aluminum metal with a diameter of 12.5 millimeters and a mass of 16.559 grams, you know its density to be 2.70 grams per centimeter cubed. What is its length in millimeters? Since the density is given to you in grams per centimeter cubed, my suggestion is convert the diameter into centimeters, then work with getting your radius, then end up converting back into millimeters. So you should get as an answer that your length of your cylindrical piece is 50.0 millimeters. And then the last one is a giant solid sphere with a diameter of 70 centimeters. That's a big solid steel sphere. Its density is 7.8 grams per cubic centimeter. I want you to know what its mass in grams is. So you should find that it has a large mass of 1.40 times 10 to the 6th grams. A little tidbit, that would be 1.40 megagrams for those dorks out there who want to do those kind of conversions. Okay, I apologize for this one's being so long, but just needed to get all this information in, and I hope that you make use of the chapter markers and just go to what you need. Okie dokie. Again, if you have questions and I don't teach you, certainly email me with whatever questions you have. I appreciate your listening and your watching, and look for more podcasts to come your way. Thank you. Bye.